Let's have an overview of all the three laws, Kepler laws, starting off with the first law, law of orbit. Second law is to do with law of area. And third law is to do with law of period, right? Time period, basically. Law of orbit. So we learned about ellipse in the last video. You guys need to understand this diagram before we can move on. See, sun is either in F1 or F2. Basically, wherever sun is there, we consider it as F1. So it's either located in one of the focus. The closest point through which the Earth passes the focus is known as perihelion. Diagonally opposite, you have aphelion. So these are the two words that I didn't introduce in the last video. But yeah, here it is. So again, wherever the sun is, that's where you have your F1. So in this diagram, my F1 is over here. So you can imagine that the sun is over here. And the planets are taking the path which is described by the ellipse. Okay, so that has to be very clear. Planets do not move in a perfect circles. Their path are ellipse. And the sun is not at the center but at one of the foci. All planets move in elliptical orbit with the sun at one focus of the ellipse. So this is the first law, simple and straightforward. It's just telling not circle but yes ellipse. And sun not at the center but at one of the focus. Okay, next. Second law, law of areas. This we have to prove and all mathematically. So basic idea is that a planet moves faster when it is closer to the sun and slower when it is further. But the rate at which the area is swept out is always constant. So given an ellipse, right? So this is a line connecting from the center to the planet. Okay. So when it moves from one end to the other end, say in a month, it covers this much of distance. The area, shaded area over here, will be equal to the shaded area over here. So you can see 1 month, 1 month. A1 and A2 will have the same area. Okay, so I will explain with the screen per se. Let's do this. Ellipse, one of the focus, fixing the sun over there. So a planet is over here. It covers, say, okay, planet is over here and it covers this distance within a span of, say, 20 days. I'm changing the setup so that you guys can get the variation. So this is 20 days, for example. Again, don't think of Earth, you can think of anything else. And say this is 20 days over here. So if we figure out this area, so this is area A1. This is area A2. So these two areas are equal, as simple as that. So how did we get this area? All we did is we took starting day after 20 days where the planet is, connected a line from the planet to one of the focus. So of course this focus is not one of the focus, to the sun. It is at the focus. So this is basically your arm, right? This line is your arm. So it is in this manner. So this is for 20 days. Okay. So I'm doing this and the arm will be something like this and it would be, okay. It would be so, and then this would be so. 1, 2 or 20 in this case. then so many days, x days, then this is after x days, x plus 20 days. So this being the scenario, all I have to do is you take up any 20 days. The area will remain the same. So guys, common sense. If the height of a given triangle is short, the base has to be bigger for it to have bigger area, right? If I consider these two areas are same, for these two areas to be same, like say this base is 10 centimeter and height is 2 centimeter. This height has to be 10 centimeter and the base has to be 2 centimeter for them to have the same area. You guys agree? So that's the relationship. So here the base is small, the height is bigger. Here the base is bigger, the height is shorter. So that commonsensical point will help you understand this. So I'll write way to understand. A synonym of sort. So for a short based triangle to be equal to triangle's area to be equal to a long based triangle, the height has to be longer in the first triangle in comparison to second triangle. Again, commonsensical point. Okay, so that's your second law. So this will be proving actually. Line joining a planet and the sun sweeps out equal area in equal interval of time. And your third. So law of your time period. Planets that are further from the sun take much more longer to complete one orbit. This is a precise mathematically relationship between a planet's distance and its time period. So basically, square of the orbital period of a planet is proportional to the cube of the semi-major axis of its orbit. So you remember semi-major and semi-minor, right? So semi-major, I think I don't have it in my diagram. So this is your semi-major from the center to this point. From the center to the furthest most point on the ellipse. You can think of it that way. So it would be, we have used A also, remember? So the formula is x square by a square plus y square by b square is equal to 1. So A is your furthest point away and all of those. So this will be your furthest point. Sorry, from the center. This looks like the center. Okay, point is, further you go, more time planet will take to go around the planet. Go around the sun. So here we have 3 examples. All the 3 started at the same time. T is equal to 0. As you can see, when T is equal to 1, the planets are at different positions. And the relation is not a simple T is proportional to A. It's not that. T square is proportional to A cube. So it's pretty complex. And so you can see the relationship is not linear. Right? Clearly the relationship is not linear. So these are your 3 laws. It's very simple. First is to do with the shape, how they move, and position of the sun. Second is to do with the time period per se and actually area. So how fast, what is the pace at which the planet moves, depending on the position. Or if you want to call it as law of areas, but I think better than that would be how fast, for us to realize and understand how fast the planet moves in relation to its position with the sun. Closer it is, faster it will move. Further it is, slower it will move. An indirect effect is that the area swept within a given time period is fixed. And third law is law of time period. So for a given time, the amount of the orbit's path it covers, a planet covers, has this relationship. Okay, so you have to write it. There's no other option.